5 because they all go.
Yeah. Yeah, it's 1 hour and a half. Yeah. I mean, it's flexible.
Yeah, no, I mean, I'll see how people react. If they all die, they'll stop. I mean, from the heat and the hot. Sounds good, yeah, no worries.
Right, because you have to make sure that, so a dagger actually not original encoding, it produces the same effect as exactly as the volume. And that, so for example, a dagger wants some backwards state. Yeah, that's it. Now, so I got like this feedback like I'm going to be explicit on this. And this is one. So okay. So you should look at the Jordan method. This basically goes something like. Yes. Yeah, well, no. Okay, it doesn't matter.
Just remember, every time you want to show a slide, remember to share the screen, and when you want to switch to Blackboard, unshare the screen.
And then I'll let you know also.
Yes, when you want to switch to the Blackboard, just let me know, and
Yeah. Thank you.
Yeah, so maybe you can
All right, so let's maybe get started. So welcome to the second lecture of the day. So I'm going to give the first lecture on variational quantum algorithms. The second lecture will be tomorrow, given by Leonardo. So let me start by, welcome you here. I mean, you were already welcomed by others, but for myself, I'm very happy to meet you all, and I'm very thrilled to explain to you some of the things that I've been working on over the past couple of years with colleagues and Ames and at Fermilab and other places. And I mean, quantum computing is for me a really great endeavor to meet a lot of new people. I'm traditionally a condensed matter theorist, so I'm meeting a lot of people with other backgrounds in computational physics and nuclear theory. So it has been really very fruitful, and I'm looking forward to more interactions here and elsewhere. Okay, so let me start with a few slides, and then I'll give a Blackboard talk because you are field theorists. So, I mean, at least some of you are. Okay, but so this first slide is kind of like a summary of what I will be talking about, which is from the review, from a review that appears in a journal that I have no access to. So I checked the archive version, but it's a pretty good review by a lot of people, and it summarizes in Figure 1 what variational quantum algorithms are. And so actually, there I can use this pointer. Okay, and so let me take 2 minutes to go through this. So the idea is that you are combining the computation power of a quantum computer with the computation power of a classical computer. So it's also called a hybrid quantum classical algorithms. And it's kind of well suited to an era where maybe the quantum computer has limited capabilities like now, and you want to use it for a specific task in a calculation and outsource that to the quantum device and perform the rest of the task on the classical computer. And so this works as follows. So, I mean, the reason it's called variational is that typically you prepare a certain quantum state on the quantum computer, which, in practice means you apply a circuit that has gates that have real parameters that parameterize rotations, for example. So you could just have a circuit as shown here. I mean, it's a little small, but has C0 gates, which are not parameterized, but then maybe single qubit rotations by some angle theta. And these angles theta, they are the variational parameters that are, that characterize your state. And, when you vary theta from 0 to pi or so, then you basically create a manifold of variational states, and you can create those states on the quantum device. If you limit yourself, to quantum circuits that you can realize on these devices, which limits the circuit depth and circuit width, of course, because we know we can't correct for the errors that occur. So you can only realize certain states on the quantum device, but that is also ideally tailored for only looking into variation states, but that with a high fidelity you can actually produce on the quantum device. So once you have created that state, you can measure the qubits, and that effectively means you're measuring an observable. So think about, for example, the energy of that state with respect to some Hamiltonian, or you can look at other cost functions or other observables, and I'll give you more examples later in the Blackboard. And once you have that observable, that's just a number. Then you feed that. I mean, here's the C of theta. So that observable will be a function of all the variation parameters that parameterize your state, and you can feed that into a classical computer, which then, I mean, as a function of theta, there will be a landscape how this observable will look like. And maybe you want to find the minimum of this cost function, right? So for the Hamiltonian, that would then give you the ground state energy of this problem within the variational manifold. So then the classical device will actually compute that, perform that classical minimization and try to find the arc min of that cost function, which is what you're interested in. And well, while you're doing the optimization, of course, you need to evaluate the cost function again and again. So what the classical optimizer will do, it will suggest an updated step to new parameters theta, and then you will again run your circuit, compute the observables, and feed it back into the classical device. So there's a feedback loop, typically, not in all of them, but in most of in most of variational algorithms, there's a feedback loop, this hybrid loop here between a quantum calculation on the quantum device and a calculation on the classical computer. And so, that's also, let me point out two difficulties with this approach already at this point. So the first one is that you have to have a very efficient way that this feedback loop can be done in practice, right? Because you need to run it many times. This optimization will potentially involve many updates, and so you need to be able to do that relatively quickly if you want to run this in practice. And the second problem is that you need to do a lot of measurements. So basically, what you're doing in these algorithms, you're trading circuit depth because it's limited by the fact that you have errors that you can't correct for by making many repeated measurements. And so that's typically the limit or one of the bottlenecks of variation quantum algorithm that you have to make a lot of measurements, which takes time. So, and you need to make a lot of measurements because, you know, as I said, you create that state, make measurements in every of these steps. And of course, you need to measure this more than once because, you know, you have shot noise, and I'll talk a bit more about that later. Okay, but then apart from these caveats, the output could then be, you know, could be the gate sequence that prepares the ground state or like approximates the ground state. You can get ground state energies. You can get other things out of this. Okay, so this is my 5-minute summary of my whole lecture. So, you know, I'm a realist. So 1.5 hours is a very long time to concentrate for me. I don't know about you. My attention span is adjusted to, you know, 10 to 15 minutes. Anyway, so I don't know how you're gonna suffer through that, but that's why if you from now on kind of zone out or something, then you got the main idea. All right. So now I'll take 2 slides and then I'll go to Blackboard to tell you a bit about AIMS. So I'm an associate professor. I should have said this in the beginning. Sorry about that. I'm Peter Orth. I'm an associate professor at Iowa State University. I'm working there since 2016. And Iowa State University is a land-grant university. So it's a state university in the state of Iowa that I'm sure you're all very familiar with because, you know, it's in the center of the US, and, you know, I mean, a famous president said he's going to make Iowa from a fly-over state to a fly-to state. So that has not happened. But still, it's pretty nice. If you fly over it, just look over it. It looks like nice cornfields, long roads, and it's pretty nice there. I'm just joking, okay? I'm from Germany originally, so I don't have any problem making fun of Iowa. But I mean, I lived there since 6 years. I'm very happy. Life is pretty simple there. You have like no commutes. You have great people there at the university and in the city of Ames, so it's a very nice place. And this is the National Lab, Ames Laboratory. It's focused on materials research, so we grow some of the cleanest rare earth materials, but recently we also have some efforts in quantum computing, and I'm part of that, but there are also others. It's the smallest of all the national labs, which, you know, is actually, in my view, an advantage because it's just opposite. So on the other side of this nice parking lot, there is the physics department. So you can just go over and meet colleagues there. We don't have any badges, and everything is it just basically gives a lot more infrastructure to the condensed matter and like materials, simulations, computation physics department at the university. So it's kind of like a booster for the university, for the physics department. And it brings a lot of potential for like collaborations as SQMS and others things. Okay, so this is the national lab, this is campus, and this was my group earlier this year when half of the people were in isolation, but anyway, so this is the other half. And I want to have one more slide of like other people at our university who do quantum computing. If, you know, as a postdoc or so, you consider that as an option, then I can recommend, apart from me, of course, these 3 folks. There's Tom Iadecola, who's my colleague, who's also part of SQMS. He is an assistant professor, and he's an expert in non-equilibrium dynamics, topological field theory, quantum computing. So he has a recent Nature paper with a Chinese group where this it was from the press release. So you should check it out on Floquet systems realized with quantum computing. There's Srimoni Sen. She is a nuclear theorist. She's the closest to this Galileo Galilei Center, I would say, from her background. So she's working on QCD, quantum field theory, and she's also interested in quantum computing. And Yongjin Yao is my colleague who is also working with me on a separate DOE grant on quantum computing, and his background is material simulation, computation physics. And here is one of our joint group meetings. So we have a lot of, I mean, we're kind of the same age, so we have a lot of like joint group meetings, and so it's kind of nice to be there. Let me just mention, Ames Lab participates in 2 National Quantum Initiative Centers, not just SQMS, but also another one called CTQA. And in general, there's a strong collaboration across fields between theory and experiment at our lab. Okay, so with this, I will switch to the Blackboard. All right, so I'll first cover variational quantum algorithms for ground state preparation, and that's going to be actually 99.9% of my lecture. And I'm going to specifically cover two different two different ways to do that. One is I'm going to compare gradient descent to what's called the quantum natural gradient descent. So it's a method to perform this optimization that I said in the beginning. And I'm going to cover how it's related to quantum imaginary time evolution. Actually, I don't know how in nuclear theory do you do imaginary time evolution? Is that something that seems common, right? Also for you guys? Hank would, right? You have to tell me. I think so, right? So like for ground state preparation and so on. Anyway, so like you can also do quantum imaginary time evolution on a quantum device, and that gives you the ground states, and there's a relation to this quantum natural gradient descent. And then I will show, actually, yeah, if you do this variational, you can call this variational quantum imaginary time evolution. And then I'm going to show you a different way of arriving at the same equations based on some variational principle that will basically give you, this variational principle gives you a classical equation of motion for the parameters theta as they evolve along the imaginary time evolution path, or similarly along the real time evolution path. And that's kind of the final outlook that I will end with, is like VQAs for real time evolution. And there's like a similar kind of like Mclaren principle to derive very similar equations for the parameters theta as a function of real time. And in the unusual event that I have more time, I can show you also alternative methods. Yeah.
What's the
The what? Mclaren? Yeah. Actually, yeah, I didn't make up this name. This is a person from the 60s. Yeah. So. But you know, I follow what other people do. Yeah, so I'll also address a bit like the issues that arise from shots and so on, but this just gives you like oh, nice, the overview. Okay, so I already said in words what is a variational quantum algorithm, but let me still write it on the blackboard. So I would say you write down a parameterized quantum circuit, which gives you a wave function. Okay, this is very noisy, but sorry. Psi of theta, which is obtained. And let me write this once that this is a vector, but I will not keep that because you're not undergrad. So, but this is not just one parameter, right? This is a collection of parameters, and it acts on some reference state, which is easy to prepare. So you can think of this as the all zero state, but it could also be something else, yeah. But it's just a fixed reference state that you apply. So you have to pick a reference state. You have to pick a parameterized quantum circuit, and we're going to discuss a bit how you can pick that. And there are many different ways. So you see already that I mean, that variation quantum algorithms are to some extent very heuristic, because what I will find depends to a large extent on my choice of this U of theta. So if I just pick the wrong ansatz, then I probably will not find the ground state, or not. I will not be able to get a good approximation of the ground state. So it's in some sense heuristic, but again, the advantage is that you can constrain yourself to circuits that you can actually execute with high fidelity. Okay, so then, as I said, the idea is you determine these parameters theta by classically optimizing an objective cost function. And so let me give you some examples of cost functions. So the first one I already mentioned. This would be, for example, the energy. So you look at the expectation value of a Hamiltonian. So I'm a condensed matter theorist. So for me, the Hamiltonian is known. It's just because we have the theory of everything for electrons and so on. So it could be a fermionic Hamiltonian, maybe electrons in a solid, or a quantum chemistry problem interacting electrons in different orbitals. Or like what I'm more interested in, it could be like a spin model. So it could be interacting spin 1/2 or spin 1s on a lattice, describing a magnetic material. So it could also be bosonic. So this is like very general in some sense, right? But I can basically evaluate a Hamiltonian, which I will translate all of these into a sum of Pauli strings. This will be my Hamiltonian with some coefficients that I determine classically. So the Hamiltonian is given. And then I compute this expectation value, and this is my cost function. And so if I then optimize this cost function, I will find the lowest energy state if I minimize it, right? So I will find an upper bound to the ground state. All right, so this is one example. So another example is I can also take as a cost function the energy variance. Yeah, I sometimes change notation here, but I think it'll be fine. Maybe the board is better. So this is the variance of the energy. So now you can tell me, like, when is this cost function minimal? Where would I converge to if I manage to reach a minimum of this cost function? What have I achieved? An eigenstate, right? Any eigenstate, right? So this is a minimum for any eigenstate. So that means I can now prepare potentially other eigenstates. Excited states, arbitrarily highly excited states. There's some caveat to this because excited states can be very dense, and so it's going to be not easy to prepare in a singular eigenstate. But even like you could, for example, run this minimization program to like up to some convergence, and then you will basically maybe you will get a superposition of a few eigenstates or so. So that's another example. A third example is you can also say, well, I not just want any eigenstate, I want it to be in a certain energy range. So you can minimize this cost function. So this is basically, let me just, for lack of time, we call this C1. This is a bit arbitrary, but this is C1 plus H minus lambda. So this will now, this will now optimize the sum of the energy variance. So I want a small energy variance, but I also want the energy to be close to lambda. So this is called the folded spectrum method. This was already discussed in the very original VQE paper from Peruzzo, I think. And so here the idea would be you target an excited state at a given energy lambda. And so now again, if you run this, not until you have like a single eigenstate, you can maybe generate something like a microcanonical ensemble, right? Where you are guaranteed that you basically convert, you're trying to like minimize the variance, which means you're only collecting states that are nearby that lambda. And so it's basically like something like a microcanonical ensemble. So you can do statistics with it's like a, you can do statistical mechanics with this method, for example. Okay. Okay, so finally, the last cost function that I wanted to show you is a different one. And this is this one here. So write it. So this is called the infidelity. So it is the infidelity with a given target state. So let's say you want to prepare this target state, and if I minimize this, I maximize the overlap of my state psi of theta with a known target state. So I mean, this part here would be called the fidelity, and 1 minus that is called the infidelity. And so here, basically, you can you're trying to prepare a specific target state, which can also be useful. Okay, right. I can post my lecture notes later. I have a bit more how you actually do this in practice, but I think I'll skip that. You can read that later and discuss with me. Maybe let me just go through the beginning here. So one way to, well, you can ask the question, how would I actually measure this on a quantum computer, right? I told you these things are pretty okay, right? These are just like observable. These are just Pauli strings. So now, like Hamiltonian, I said, there's a sum of Pauli strings. You know that you can prepare that state and then measure expectation value of Pauli operators, and then you just sum them up. Those that do not commute, that gives you this expectation value here. But how do you do this? So here the idea is you can measure, for example, I mean, there are many different ways of doing this. I mean, not many, there are a couple of different ways. One is a swap test. You can like, but that requires some ancillars and it's a bit difficult on NIST devices. Another one is that you basically, you can write this as, you know, reference state. Maybe you have U dagger target, then U of theta reference state. And so you can think of this concatenating these two circuits and just measuring the return probability to your initial state. So you're preparing a certain bit string, let's say all 0 or whatever you want. You apply your variation state, you apply the inverse of your of the target unitary, and then you measure the probability of going back to the initial bit string. So if you optimize that, then you're optimizing this. So that would be a circuit that's twice as long, not twice. It's like concatenating these two circuits. Yeah, question? No, U target is given here.
But if you know your target, don't you know what you need to prepare?
Sorry, can you please repeat the question?
Oh, right, yeah. So the question was, if I know U dagger target, would I know what to prepare? Yes and no. So you may still want to compress that unitary into another unitary. So yeah, if you don't know how to prepare that state, there's no way a quantum computer can compute it for you. But yeah, it's a very good question. But the idea I have in mind, and this is like that this U target is, you can do it, but you want to achieve that state with a shallower circuit. Okay, so that's the idea. Very good question. Yeah, yeah. Oh yeah, it's just this inner thing here. Over here. End of the second line. This should be a square. Yeah, you're right. I just need to double check what I'm doing. So at the board, you know, I cannot calculate. I already, well, I can, but you don't want to suffer through that. Okay, so now let me discuss a bit, and let me just write it here, return probability. Okay, so now let me spend a bit of time talking about different strategies to select an ansatz, U of theta. So there are typically 3 classes. The first one is called hardware efficient. And so here, this depends. What this means in practice is that, you know, every hardware has some native gates, and you know they can be executed most easily. And so you're basically just choosing an ansatz that's composed out of the native gates of the device that you're running this on. So it's kind of like has nothing to do with the exact problem you're trying to solve. It's tied to the machine that you want to use. But this sometimes allows you to execute deeper circuits because you know you don't have to decompose the gates into native gates. Okay. A second one is that you can choose a model-specific ansatz. And so here, one example that I can give you is the Hamiltonian Variation ansatz, it's called. So that's a common one. And it's basically, the idea is kind of like you write down something like Schroeder evolution, but then you're promoting T to a variation parameter theta in every of the terms of the Schroeder evolution. That would be one way. So let me abbreviate this, although I mean this is called Hamiltonian Variation ansatz. So if you write the Hamiltonian, you know, as a sum of different terms that do not commute with each other, but all the terms in H1 and so on commute among themselves, and then you can write down this ansatz as like, typically you have okay, let me write it first. Typically you repeat a given layer. So let me write the equation and then tell you. Okay, I'm not good at this anymore. Okay, so the idea is this is a product of different layers, but in every layer you're going to have, okay, I should say what U is, right? U, L, I is e to the minus I. Right, so you're applying e to the minus I theta times the Hamiltonian, and you're applying for every part of the Hamiltonian that, you know, I mean, you can split the Hamiltonian into these parts, like in Schroeder, when you're doing Schroeder decomposition, I think like Sohaib probably covered Schroeder into this way, but then instead of time, you have a variation parameter and you have a different parameter for every term I, and then you just, in principle, you can repeat that structure and make many different layers. That would be this curly L here. So it's just nice to have kind of ansatz which are a little bit structured, so it's easier to grasp them, but it's like totally up to you. Okay, then there is the third ansatz strategy that I want to mention is that you can also have the ansatz grow dynamically during the optimization and let kind of the computer decide according to some criteria on how to append the ansatz as you perform the optimization. That's called adaptive ansatz strategy. And so in practice, for example, think about this way. So you're classifying operators into a predefined pool. So let's say I take all single qubit operators and all 2-qubit operators on nearest neighbor links into my pool. So then I can append terms like e to the minus I theta of these Paulis. And I start maybe from an empty ansatz, and then the criterion could be like check from all the operators in the pool, which one has a minimal, where would you reduce the gradient of the cost function? So you can compute that gradient on the quantum computer. I can show you later how. And then you select the operator that has the maximal gradient, so that you would include that operator would reduce the energy maximally. Then you append that operator to your ansatz, you optimize, and then you start again. You ask like, which operator should I add now? And so then it will basically like generate an ansatz for you. And that typically works pretty well in practice. I have a number of papers of this. The original idea was from the Virginia Tech group. So that's another way. So then you can of course like also check what ansatz did the computer generate? How does it compare to more heuristic ansatz and so on. Okay, so now after that, I want to talk a bit about the optimization strategies. Any questions? Or, I mean, this is hard to have any questions. It's just statements of stuff. Okay, so optimization strategies. And you're going to have a lab later, and where you're going to do VQE as well. This is more like for those who maybe want to play around with this. So, you know, there are basically two classes. There's gradient-based optimizers that, you know, use the gradient of the cost function, and there are non-gradient-based optimizers. And so let me just mention, you know, there's stochastic gradient descent. Actually, let me just mention them. So there's stochastic gradient descent, there's this quantum natural gradient descent, which I will discuss. There's things from machine learning like Adam. You can do this BFGS or SPSS, so you can try different optimizers that are using the gradient. So usually it's good to use the gradient, right? Because that's important information in which direction you should update the parameters. And you can actually, for certain ansatz, you can compute the gradient analytically. So it's good, you can compute them, and I'll discuss that in a second, using the parameter shift rule. And then there are non-gradient based approaches. And then here, I mean, typical ones are this Nelder meet that people used in the beginning very often. There's one called Bobiqua, and they're evolutionary algorithms where you initialize many different states and you randomly walk around, select the minimum. Yeah. So there's one difficulty that comes with this, which is, your cost function is noisy, because when you're evaluating the expectation value, you're doing this only a certain number of times. So we call that shot noise or sample noise, right? Because from quantum mechanics, if you measure a Pauli operator, even though the expectation value may be 0, you're going to measure 1 or -1. And so when you have to average over many results to get the expectation value that you feed into the classical optimizer. And because you only have a limited number of shots available, that will be a noisy cost function. And so doing noisy classical optimization is very difficult. In particular, if you have a high dimensional parameter space as we have here. So this is also classically a challenging task, but a lot of these methods have been developed also for machine learning and other things. So it's not that we are starting from scratch. So you can make use of some of the power that has been developed on the classical side. Okay, so now I wanted to explain to you how you actually compute gradients on the quantum computer. Right, what's the time? So can you remind me, when did I start? At 15 past, right? Okay. Okay. That's fine. I don't want to, at some point, it's only me who stands between lunch, and I don't like that. So parameter shift rules to compute gradients. So this works for certain ansätze. So let me. It's a little bit more general than what I will use here, but let me confine myself to ansätze of this form, which are also very relevant. So it's not too bad. Which are products of e to the minus I theta I pi, where pi is a Pauli string. And the HVA falls into that class if you write HI as a sum of a Paulis, and then here we're choosing the same parameter for many different Paulis potentially, but you don't have to. But yeah, so that would be the class where I'm confine myself. In principle, this can be relaxed to any Hermitian operator with just 2 eigenvalues. This rule. So this rule was put forth by Matarai and Maria Schult. Mitarai and others, and Schult et al. So the idea is right. So the energy, as I said, is given by this expectation value. So I'm going to rewrite this as my reference state. Let me maybe call the reference state 0 for now, so it's easier for you to distinguish it from psi of theta. And then I'm applying these unitaries. Now I'm going to define a state psi I minus 1, which I think is self-explanatory. And then I have this object I plus 1. Right, so this psi I minus 1 is basically combining all the u's from 1 to I minus 1. And this h is like combining all the u's between I plus 1 and n to the Hamiltonian. Yeah, because let's say I'm interested in computing the derivative with respect to the parameter theta I that shows up in this u dagger I. So if I want to compute e theta I of e of theta, I can easily see that this is, this brings down a I pi on the left, and then, I'm just using the product rule, right? So I'm taking derivative with respect to this, plus derivative with respect to this. So this is I pi times this, and this is minus I pi on the other side. So then I think you allow me to skip to this, move to this thing. So this is the commutator of pi with this Hamiltonian, this stressed Hamiltonian. And so now this Hamiltonian, this commutator I wanted to say, you can actually rewrite because this is a Pauli. So we're going to use that e to the, let me just do it, and then so we can write this commutator. I'm going to write like this. That's just the definition of commutator. And now I will write it like this. So 1/2 1 plus I pi it's 1/2. And I can post my lecture notes. So if this is a bit too much for you to write, then like this. So it's not, you just have to multiply it out and see that it works. And then the idea is that this here is square root 2 times e to the minus, this is actually plus e to the plus I pi over 4 pi, right? So we're using, what we're using here is that, e to the I theta p is cosine theta plus I p sine theta, right? So this is only valid for Pauli operators. So this is what I'm using here, and then you can rewrite this in terms of a rotation, and you can rewrite this and this and this. And the idea is, of course, now I can combine this rotation, which is of the same form as on the left of this. On the left of this term here, there is already a rotation by some parameter theta I, and I'm just going to shift it by pi over 4, right? So I'll write it down, yeah. And then on the right, similarly, you also have a shift that you shift this one with. So in the end, it's going to be of exactly the same form, but with these parameters being shifted by plus minus pi over 4 in these two sums. And so you add and subtract expectation values that are computed with in the same way, just you have shifted values of this particular operator that goes into UI. Okay, so let me show it explicitly. Here, so. This is dagger 5, 4. So this is the first term. Yeah, and then you subtract the second term. I don't want to close this. Sorry. So you subtract the second term. Okay, so this is how you compute the gradient, right? You can see that the gradient, you can compute it in the exact same way as you compute expectation values, right? And this is the exact gradient. So this is an analytical result for the gradient. Of course, I mean, these will be affected by shot noise, but other than that, this is much better than using the finite difference method, right? You can imagine if you can also say, well, let me compute the gradient, how I learned it in school, right? E of theta plus epsilon minus E of theta divided by epsilon. The problem is you only know E of theta up to some shot noise, yeah? So if you add an epsilon to that, you need to make sure that you know it better than the infinitesimal epsilon, which means you typically don't know that. So you can't easily use the finite differences here. So here, it's an analytical result and you're shifting it by some finite value pi over 4. Okay, so this is the parameter shift rule, and that means it's totally fine to use gradient-based optimizers. You just feed in this cost function if you have an ansatz of this form. All right, so then I think in the remainder, are there any questions or? Yeah.
How should we choose the number?
The what?
How should we choose the number and theta?
The number and theta? Ah, yeah. So again, this is very, oh yeah, he's out. Sorry, there was a question, how do I choose the number of variation parameters in theta? I think this is depends on your ansatz, yeah. So like, I mean, like, I cannot answer that in general, right? So I mean, like for the HVA, so basically you probably don't want to choose it very large initially, and you see whether you can get away with an ansatz with not so many parameters to optimize. And then if it doesn't work, you make the ansatz deeper and deeper, depending on how difficult the state is that you're trying to target. For the HVA, I had this, for the Hamiltonian Variation ansatz, I had this layer, right? This layer L that you can just make more layers. So typically, you also find that these gradients in practice, and I think Leonardo will talk about that in more detail, in practice, these gradients could be exponentially vanishing. And so you want to maybe add more parameters to kind of over-parameterize your state, similar to machine learning. So that could be in principle pretty large, but in practice, if it's larger than of order 100, it becomes kind of impractical to do the optimization. So it's like between, I don't know, 50 and 100 or so, or 200 or something, yeah. Good question, thank you. So then, any other questions? I think I can. Okay, so we covered the first bullet point, so that's fine. So now let's talk about quantum natural gradient descent, because it's like a nice method, and it also connects different methods that are being proposed in the literature. So I think it's a worthwhile like not knowing about this. So this was proposed by Stokes et al. Giuseppe Carleo in 2019. So the idea is, when you're using vanilla gradient descent, your update rule. Actually, let me call this vanilla gradient descent. Then the update rule that you would do, and I mean, okay, maybe I put in the vector now sometimes, but I'm not sure. from optimization step t to optimization step t plus 1 would be that, you know, you are walking with a certain step size eta into the direction of the gradient of the cost function at time t. All right, this would be the update rule you're using for vanilla gradient descent. So you can compute the gradient of the cost function at this for these variation parameters at optimization step t. You fix a step size, which is a hyperparameter that you can also vary during the optimization. So you're saying walk in that direction with that step size, and that these are my new parameters. Okay, this is vanilla gradient descent. You can actually you can reformulate this update rule also, which will be useful, as like the following way. You can write this as the arc min over all theta of the following. So with this bracket, I mean the scalar product. I think you've probably seen this before, right? So this is the Euclidean scalar product between these. And then this is the norm and squared. And let me be specific that this is the L2 norm. So it's just a regular norm, like the size, I mean, the sum of squares of these vectors. So, so finding the argument of this is the same as this, which you can easily show if you just take the first order derivative of this, you find this condition. Okay, so it's really easy. You just say, yeah, d theta I of this equation gives me this. Okay. So in other words, qualitatively, it says like, okay, I want to walk in the direction of the gradient minus the gradient, but I also don't like to end up far away from theta t up to some step size. Okay, so that will be useful for us because what the gradient natural gradient descent proposes is that in fact, instead of using the L2 norm here, which is just the Euclidean norm on the space of variation parameters, you're actually going to use a metric that is defined on the variational states themselves, on the wave functions. Because, you know, that step size, I mean, in the end, you're interested in how much the wave function changes. You're not care that much about the parameter update. I mean, the parameters are just like some classical parameterization. But, you know, you probably want to choose a step size according to the real geometry of your problem, which is on the space of variational states. And you can define a metric on pure states. And it's called the Fubini-Studi metric, and then you can use that metric here for that norm instead of the L2 norm, and that basically reflects the fact that you're putting in, if I'm updating parameters theta 1 and theta 2 in some direction, the change of the wave function may be different, because the metric, I mean, the wave function may change differently if I change parameter theta 1 versus theta 2, whereas here this Euclidean 2 norm would just square both sums up and doesn't know what effect this has on the wave function. Okay, so let me therefore, because I think this, the reason I chose this also is because this Fubini-Studi metric like shows up in many different parts of physics, and I think it's just a nice thing to know about. And it's pretty general. So, I mean, I know who here has a condensed matter background. Is there anyone who has a condensed matter background or study? Okay, so there's a minority of people like me. No, I mean, in condensed matter, let me just say, it is like it's really like something that has come up a lot in the recent years in many different fields, like in superconductors, in nonlinear optics, and transport, and quantum Hall physics. I mean, I'm sure it also shows up in fraction quantum Hall physics. I'm sure it also shows up in many other fields. So, okay, so let me define let me define this this metric on the space of pure states. So it's defined like this. So the distance between, I'm going to use the notation here from the paper. So if you read that paper, you're going to recognize this notation. I thought that's kind of useful. So let me write it and explain it to you. So this p psi, it's just a pure state, so it's a projector. Yeah, I don't have to write p phi. So, right, you know that, I mean, quantum states are defined as complex projective space. So your global phase doesn't matter. So you have these rays, and you can ask, what is the distance? What's the distance between a quantum state psi and a quantum state phi? And you can define it as the Arcus cosine of this absolute value of the overlap. Okay, so it's pretty easy. So I will not prove that this fulfills the properties of a metric, which, you know, the only difficult thing is a triangle inequality. So I convinced myself by looking at plots. I was kind of not able to do it analytically when I prepared this over the weekend. So to be honest with you, it shouldn't be that hard, but somehow I gave up. So this is the first property of a metric, that, you know, you want the metric to be 0 only if the states are identical. So this is just generally if you define a metric like in pure math or so. The second property of a metric, that it's symmetric. And the third property is this triangle inequality. That means if you go from psi to chi, but you go via phi, then, you know, it's going to be at least as long as the direct way. So this is a triangle inequality. And so you can kind of intuitively understand why this works. So if I'm just plotting this Arcus cosine function as a function of x, the overlap, this will be between 0 and 1, right? Because it's the absolute value. So, okay, this doesn't look exactly like that, but roughly speaking, this is pi over 2, and this is 1. This is 0. This is 1. So you see, if the overlap is 0, then they're maximally separated, which gives me a distance of pi over 2. And if they are the same, so the overlap is 1, then the distance is 0 as it's supposed to be. Okay. So this distance of pure states will be between 1 and pi over 2. And I thought, like, what would be a nice exercise is actually if you take like single qubit states on the Bloch sphere and do that and relate that to like the arc length or so. I mean, if you're interested in doing some kind of exercises, I mean, I know there are lots of lectures and it's hot and you also want to socialize, so you can do that when you're back and bored to death at home. But yeah, I think that would be a fun exercise. So you take this to be like general single qubit states on the Bloch sphere and relate this to the distance of the thetas and phi. Just gain some intuition. Okay, good. Any questions with this? So now I want to now derive this an expression for this metric. So how much between nearby states. So I'm interested in deriving. It's easier to do d squared, so it's a metric squared. But between a variation state of parameter theta and a variation state of parameter theta plus delta theta, I'm going to show that. And depending on time, maybe I'll skip some of the steps, even though I have them all here. But this is this Fubini-Study metric. Actually, let me know, in the interest of time, I'll just going to give you the results. I have the derivation here, and it's kind of fun to do that. You have to do a Taylor expansion and use some identities. So let me show you just the basic things. So I'm not going to go through everything, but the idea is just because of time. Otherwise, I do it. But so you expand this in Taylor expansion. So you're saying psi of theta plus delta theta is psi of theta plus psi of theta d theta I delta theta I plus 1/2 second derivative this is sufficient to the disorder. And then you're going to use some identities. And again, since I won't show it to you, this is a nice homework. One identity that comes from the fact that psi is normalized. So if I take the derivative on the right-hand side, it's 0. If I take the derivative on the left-hand side, I can use the product rule. So I'm going to get the following. Plus. What is this? Yeah, so I can also write this. Of course, this is the Hamiltonian complex conjugate of this one, right? So this is like psi of theta, deep psi of star. So what does this equation tell me about this quantity? If you take a number plus its complex conjugate, and that's 0. What does this tell you? I got you. You're all sleeping. Maybe not. Any, I mean, Yeah, it's purely imaginary. Exactly. Right, so, I mean, maybe it's like, maybe I should have written this too. It's a bit easier. Okay, so this tells me that this is purely imaginary, right? Because z is equal to minus z star. Okay, so that thing is purely imaginary. So in physics, I mean, maybe this is a question only for the condensed matter people. Since it's purely imaginary, we typically define this as this. So we typically write this as minus I. Oops, great. So we pull down the minus I or plus I explicitly, and we define it like this here. Okay, should have. Let me put it over here because it's kind of important. Not for us, but in general. So this thing is real except from this I, right? So from the condensed matter people, do you know what that is? This is a difficult question if you haven't seen it then. Exactly, yeah, it's a very connection. Yeah. So this here is minus I times what we call the Berry connection. So this is a very important quantity. I mean, not just in condensed matter, right? So I should not say that. Yeah. So this is the Berry connection, which I mean, from condensed matter, it gives you like, you know, the Berry phase and contributions of the Berry phase. And so the idea is like this Fubini study metric is basically is the real part of a metric tensor, where the imaginary part is like the Berry curvature. So these two are kind of related, and maybe you've known, like, have heard about all this talk about topology and condensed matter material science, and this was all driven by the Berry connection and the Berry curvature. But more recently, people have realized that also the real part of this metric tensor, which is the Fubini study metric, has important implications for the response of a material, and that's why this shows up now, kind of. So they're kind of related. I mean, one is the imaginary part, one's the real part. Okay, so so this is one identity, and you can derive something. If you take another derivative of this, which I won't do now, you can derive another identity, which you use in the derivation. And then if you do all that, and you plug this in, and you expand the arc is cosine squared, and then you group things, as you can see in my notes, we're going to arrive at the following expression for the actually, let me just give you already up there, the expression for G. So what you find, I like to show things explicitly, but this is a bit too long now. You're going to find the following expression. This real part of this derivative here minus times So it's a sum of these two terms. This is also purely real, this term here, because each of this is purely imaginary, and so the product of two is real. And so this is real, and this is real, and so you can actually define this is the real part of an object, which is this capital G is called the quantum geometric tensor. And so if I would compute the imaginary part of this, I would then get the Berry curvature, or the Berry flux, for those infinite matter. Okay, so just to recap, what I've derived here is the Fubini-Study metric, the explicit expression on the space of. I mean, this is an expression like, this is an expression for the metric on the space of pure states, and it is actually, yeah, it's unitary. It's the only unitarily invariant metric, which means, you know, for us it's important because the variational parameters, sorry, the variation state you may reparameterize, and you know that may give you very different distances in parameter space, but not in the space of states itself. And so this is invariant under reparameterizations because it's a metric on the pure states. So it doesn't depend on it gives you the actual geometry of on the Bloch sphere, if you want to think about it this way. All right, so now once we have that, sorry, again, when is it started? It stops at half, right? Or 45? Okay, I'll stop at 45, right? Is that roughly, yeah? Okay, well, I think people are getting a bit drained by the heat and okay, so now, as I said, using this metric, we can actually define the quantum natural gradient descent update rule, which is you take the parameter theta t plus 1, which is the arcmin over all theta of theta minus theta t in the gradient direction. So you still walk in the gradient direction, but I'm saying I want to walk a distance which is given by the g of theta here. Okay, so it's at the end of the board, but it's very important. So let me use color here. So this is the difference. Right, so I'm evaluating this with g. So that means like, do you know this notation, or should I define it? Or let me just write it explicitly. So this it's basically theta minus theta t g or if you want to do it explicitly, like it's let me use Einstein summation here. In Einstein summation, that you are like high energy people, so you only know the Einstein summation. You have to explicitly say if you don't use it. Okay, so with this, we can now get the first order optimality condition. So again, we would take the derivative of this arcmin, of this arcmin equation here, and set it to 0 to find the arcmin, to find the theta. And this gives us an explicit rule for the update. And so that would first order optimality gives me that g of theta of t right. And actually, you know, let's take a brief moment to look at that. This form of the equation, which, you know, means you have to compute the metric, which you would do on the quantum computer. compute the gradient, which you would do on the quantum computer. Then you have a theta of t, which is your current parameters, and then you obtain a theta of t plus 1 by solving this linear equation, like using Python, like using your classical computer, right? So, and actually this is the general form very often of these variation quantum algorithms that, I mean, as a function of time. I mean, so this parameter time here could be the iteration step, but it could also be a physical time. So when you're deriving, which I will not have time to, but if you're deriving like how a state evolves under the Schrödinger equation, you can derive, and you wanna capture that by updating variation parameters. You will derive a very similar rule here for the parameters theta, how you should update them to follow the exact time evolution of governed by the Schrödinger equation, for example. So this is a very general form. There's one problem with this, which is that this may be ill-conditioned, and it's typically ill-conditioned. So you can also think I need to put it as an inverse over here because I'm interested in solving for theta t plus 1. So numerically, it's better to solve this linear equation, but it can still give you some problems. So sometimes one regularizes this. So you define the g. Just if you do this, I mean, for fun, and then you realize this, then I want to tell you this. So we can add some little parameter, which is much smaller than 1, because these entries are typically of order 1. So this would be the generalized inverse that you have to use here. And you can write, yeah. Okay, so now in the remaining time, so I have, let me make a selection here. So I think you guys are getting a bit tired. So so there's like two things that, so what I still have in my notes is, what I think I'll skip that, is that actually this, you can get exactly the same, I'll skip the details. You can get exactly the same updating rule. Yeah, you have a question? Yeah. Oh, so I think this has nothing to do with the quantum. The question was like, what is the, provide more intuition about why is it advantageous to use this quantum natural gradient metric versus the vanilla gradient, where the difference is that, we are taking a step size of size eta, but it's with respect to the L2 norm. Yeah, I think the way I'm thinking about this is that, you're trying to converge to a particular minimum in the space of pure states. You don't care that much about, so let me maybe, I don't know if that helps. So let's say you're at you have some parameter theta t, and the gradient is in this direction, or minus the gradient, and there's some step size eta that you want to take. And so in parameter space, so if this is like theta 1 and theta 2, this is how this would look like with vanilla gradient descent. So you go in the direction of the gradient by a distance which is given by eta. Now, if you use the fact, but the thing is like if you like states on this circle, for example, they will not all have the same. Distance in the. I mean, so here on this, let me define. So let me define some states psi of theta t plus so P of psi 2 of phi are all the states that are living on the circle, and phi is like an angle that I'm using to parameterize here. Okay, and so psi 1 is the state psi of theta 1, psi of theta t. So I'm trying to say, let's look at the distance of the states on the circle here, parameterized by parameters on the circle here, compared to the, from that state at the origin. So here in this parameter space, they all have the same distance because, you know, this is because I'm measuring distance with respect to the Euclidean metric. But if I would measure if I would use the gradient, the Frobenius-Study metric, it may look like this, for example. And so, so maybe the gradient is in this direction. And so a step size eta, you know, may actually bring me like further down here or something. So typically in practice, you converge faster to the minimum because you're using the fact that you're exploiting the actual geometry of how much you're changing the state. So it's possible that it looks like you're updating a lot in the parameter space, but the state is not changing. And then, you know, basically the distance that you should be updating is normalized according to the actual distance that you're updating the states. So you want to use that information. Otherwise, you have like no idea how large that step size should be chosen because you don't know how much it changes the states. But the Frobenius-Study metric tells you exactly that. Like if I give you an eta, how much in some direction, how much do I actually change the state? And that's what you care about. You don't care about how far the parameters are from the original parameter. I mean, typically in these updating, I'm not a machine learning expert, but these hyperparameters, you have to tune them very carefully and you have to tune them along. So the step size is not something, every step size works equally well. So you need to like change it in the beginning, it's large and it becomes smaller and so on. But this is the way it would be. It's using some information on the pure states, on the about the geometry of the pure states to select the right step size in some sense. Yeah, I don't know, is that. I mean, I wanted to give an example how this metric looks like, and we can maybe again maybe the best thing is to do like a little example on like a Bloch sphere. But I hope this helps a little bit. But I'm happy to talk more afterwards also. Okay, so now it turns out that this updating rule, according to the natural gradient descent, is in fact identical to quantum imaginary time evolution. So if you're doing quantum imaginary time evolution, then so basically you're following the path of states according to e to the minus h delta tau, which is the imaginary time evolution. You're going to follow this path. So, and I won't derive it, but I'm going to say that I'm in quantum natural gradient descent is equal to quantum, let me call it like variational quantum imaginary time evolution, because of course we are only walking in the space of variational states. We can never go to any state that's not in our variational manifold. And so basically, if you have the condition of maximizing, let me write it and then. So if you derive an equation of motion for the delta theta, an updating rule, so I should say, if you derive an updating rule for the thetas according to this condition, which means you want to maximize the overlap of your updated wave function. So you want to find the delta theta that maximizes the overlap of your variation state with that state psi bar, which is like imaginary time evolution from your original state, right? So you're applying e to the minus h d tau to your variation state at time tau, and that gives you the time evolved variational state. And you want to maximize the overlap with that state. So this is another rule in some sense. You want to apply you can derive a delta theta from there. And it turns out, I mean, again, I derive it in my notes, that it's going to be exactly the same as the quantum natural gradient descent. So this is nice because, I mean, it shows you that these two are equivalent and the imaginary time update is, well, it has been derived in literature in a different way, but this gives a nice geometric interpretation to this, yeah. Mm-hmm.
When you would do the imaginary time evolution to get like a psi theta bar, and you're leaving the complex manifold?
Yeah, you can renormalize this, yeah, but I think for the derivation you don't have to do that. Yeah, in practice, I would just use this to derive an updating rule, but yeah, you're right. This is not normalized, so I can like normalize it or so, yeah. So, but I won't write this now. But you're right. Yeah, so Right, so let me at least mention the Mclaren principle, because this is like this is a variation principle that has been used to derive these this updating rule that I'm just removing here. So if you ever see that, you know what they're doing is basically the same as what I'm. So the idea here is you want to define let's do imaginary time evolution. So imaginary time evolution, if I'm starting from the von Neumann equation and I'm replacing IT by tau, then I can derive the following equation for the density matrix. Where rho of tau I need to renormalize, I agree. So it's like e to the minus h tau rho of 0 e to the minus h tau divided by who has seen imaginary time evolution before in their studies? Okay, so it's not something that's very common, so I should not. Okay, so maybe this is not used in nuclear field theory when in other fields. I mean, in condensed matter, it's like super common, yeah, because we're interested in retarded correlation function at finite temperature, and so then this if you're doing imaginary time Green's functions, then you can do an analytic continuation to get the retarded Green's functions at finite temperature. This is like a common thing that people learn, but it doesn't really matter. So for this purpose here, I mean, like basically you can think of the von Neumann equation for the density matrix, like Schrödinger equation, and you're replacing IT by tau, you can derive this. I haven't done it for you now. And here is just basically, again, like instead of e to the minus IHT, rho, e to the IHT, you're going to use imaginary time. And here I need to renormalize that because this is not leaving the norm invariant and this is a density matrix. So now I have this, this is the equation that I want to describe. So this is an equation that governs, that shows to me how the density matrix or how the states, you can write the density matrix. I mean, of course, here we're dealing with pure states. I mean, you can derive this more general, but the derivation is easier with density matrix. But you can think of this as being just this psi here. So this is, you can still describe pure states with density matrices. So this updating, and this equation of motion describes the time evolution of the state in imaginary time. And so now I want to find, I want to update my variation parameters according as good as I can to follow this time evolution. This is what I want to reproduce. And so if I want to write this mathematically, I want to minimize the following distance. So I have, let me write the equation. So you can define this norm here, which is very intuitive. It is the difference between how the variational states change, the variational state changes. Theta dot is of course d theta d tau. This is the change of the variational state, and this is what I try to reproduce. So if I minimize that norm variationally, I can derive an equation of motion for the thetas. So that means if I follow this equation of motion, I will write it down in a second, it's exactly the same as up there. If I solve that equation of motion classically, it will describe a path in parameter space, and I'm guaranteed that along that parameter space, this distance is minimized. So this is as good as I can do in the space of my variational states. That doesn't mean I'm doing very well. You could, if like your parameterization doesn't allow to follow the exact imaginary time evolution, then that distance may not be very small. It may still be a minimum, but I'm guaranteed if I variationally derive the equation of motion, I'm going to write this down now. What is the equation? That I'm in the minimum, but it doesn't mean that that it's small. But again, the logic is, okay, let me derive the equation of motion. I mean, not derive it. Let me write it. Sorry, because I'm getting tired now as well. I'm almost done. Yeah. No, you don't. No, I'm just using this to derive an equation of motion variationally. I don't do that now, but it's in my notes. Yeah. Yeah. So there's a couple of, now it's just like math to derive what I will write now. Okay. So what you get out of this in the end. So what you're doing is you're saying, let me use this and derive the Euler Lagrange equation, which is G of theta of tau times theta dot of tau is equal to minus gradient of C of theta of tau, where the C is just 1/2 sine theta Hamiltonian. So, I mean, I already said it, that this is the same, right? So this is an equation of motion where you have to compute the Fubini-Study metric and the gradient. And you can do that on the quantum computer. And maybe in the last 2 minutes, I'm going to show the circuits and then we're done, okay? Once you have G and the gradient, it's just solving this equation. I mean, you're solving it as a differential equation. So, I mean, so that means, there's a lot of measurements you have to do because you need to compute that G and gradient at some time tau. Then you update it over some infinitesimal time step. And then you have to calculate these guys again. Yeah. So, but yeah, so this is another way to derive it. And you can do something similar in real time. The equation looks quite similar. Okay, so now I will maybe show the circuits. So yeah, so it's already over there. So, I mean, let's look at that first part here. This is part of the Fubini-Study metric, if you remember. And in order to measure this, like if I translate that into an expectation value, it's something like this, where you have to take the derivative with respect to parameter theta nu, which means that brings down this parameter at some point so you're applying the u's from 0 to mu minus 1, then you bring down. Okay, so the ansatz here. Okay, sorry. Is e to the minus I theta a mu. Okay, so instead of the p in this paper, we're using notation a mu. So a mu's are Pauli strings, and they just come down. I mean, I times this comes down when you're taking the derivative, right? And they come down at the position in the product where they occur, right? So that means you first have everything on the right, then you bring it down, and you have everything on the left, then you bring down the other one. So such an expectation value you can measure using this, like, generalized Hadamard circuit, which means all you need to do is, like, you need to apply the unitary, which is like this part. Then you apply controlled Pauli, which may be difficult, but it's just a controlled Pauli. Then another unitary, and then another controlled Pauli, and then you measure this ancilla. So this is how you can measure one element of the Fubini-Study metric. So now you can imagine if you have like n theta squared elements. I mean, it's symmetric, so you can use that, but it scales like quadratically with a number of variation parameters. So there's going to be a lot of elements you have to measure. So this is a bottleneck of this approach. And then the gradient you can measure also. You can measure with a parameter shift rule, as I said, but you can also measure with a similar circuit. And then I guess that's it. Let's not go into too much more here. Okay, so then to summarize, let me have like one summary slide here, which I think is nice. And then we'll take 1 minute, and this is what I just talked about. So here is a summary of these variation algorithms again, right? I started with this is the end. So this is now here for like regular real-time evolution, but other than that, it's very similar. So what's the idea? So we start from a variational form of a quantum state, which you can think of a parametrized quantum circuit. Here, these AMUs are Pauli operators, say. I mean, there could be something else, and so these are like just Pauli strings, and you select them, or as I said, you can adaptively generate it. And these theta mu's are your variational parameters, and applying this is applying a circuit to a reference state, gives you a certain state. You want to update these theta mu's such that this resembles, in this case, real-time evolution. So you know that we have to actually do like d rho dt is minus I commutator h with rho, which is the von Neumann equation, which in this case, you know, is exactly what I had earlier, but now you have the real time. You have the commutator here, I had the anti-commutator. And you can derive again variationally by minimizing this distance here, this equation of motion, and the matrix M and the vector V are measured. And then once you have that equation, you update it and you run this again and again and again. Okay, good. So then, yeah, thank you for your attention. I'm happy I had a bit more prepared, so I'll post my notes, but I'm happy to talk more. Thanks a lot.